Hi everybody, my name is 𝐒𝐨𝐺𝐿 and in this video we'll be discussing the next question of Codechef's April long challenge, which is squared subsequences. So without further ado, I'll be reading out the problem. You can read out for yourself if you want to by opening this link. So let's start. The question says, let's call a sequence of numbers good if the product of its elements can be represented as a difference of squares of two integers. More formally, a sequence is good if it is possible to find two integers p and q such that the product of the k numbers, that is s1 into s2 up to sk, is equals to p square minus k square. Okay, we are given a sequence a1 to an. We want to find the number of contiguous subsequences of a which are good. By contiguous subsequences, it basically means subarrays. We need to help him find the number of contiguous subsequences that are good, right? So I hope the question is pretty clear. Let's see the input format and the constraints. The first line contains test cases, the number of test cases. The first line of each test case contains the number of numbers in the sequence, and then the n spaced integers representing a1, a2 and an. Okay, for each test case we just have to print a single integer, that is the number of good subarrays of a. The number of test cases can be up to 1000. The value of n can be up to 100,000 for each test case, and the sum will not exceed 1 million over all test cases. And the values of ai can be from -1e9 to +1e9, and there are two subtasks. In the first subtask, the value of n is less than or equals to 10 raised to power 3, and for the second test case, the normal constraints that we just read. So I'll be discussing the solution this point onwards. If you want to try it for yourself, it will be a good time to pause the video. Yeah, so the one major problem that might be visible to you guys is that the numbers are really large. The numbers can be up to 10 raised to power 9, and if we basically try and store their product, it will be a very difficult task. Even if you use some classes for Java or maybe even for C++ that are able to do it, it will be very time consuming, right? Because the number of digits will be of the order 9 into 10 raised to power 5 for one product, right? Now, we don't want to basically multiply all the numbers and do something with that. So we need to come up with a condition for the product value so that it can be represented as the given expression, which is p square minus q square. Let's analyze what basically p square minus q square represents. Let's say the number that we are looking for is a, and it should be represented as p square minus q square. We can write it as p plus q into p minus q, right? Let's say p minus q is a. Can we write okay, not a, let's say small a. Can we write, and now let's say the number is x to avoid confusion. Now x is equals to a into a plus 2 into q, right? Because if we add 2 into q to p minus q, we'll get p plus q. Now we notice that if we notice the difference between these two numbers is even. 2q represents an even number, and if the difference is even, it basically means that the parities of these two numbers is same. It means that x is either equals to odd into odd, or it is equals to even into even, right? Now the liberty of choosing the odd numbers and the even numbers is with us, because we know that this a can take any possible value, and we can simply add any even number to get the second number, right? So if x is odd into odd, it means that x itself is odd, right? And if x is even into even, the additional information that we can get from this fact is that x is a multiple of 4, right? because this one for sure is a multiple of 2 and this one is a multiple of 2, and we if we add two multiples of 2 we'll get a multiple of 4, right? A multiple of 4, right? X is a multiple of 4. Now in this case we have seen that either X is odd or it is a multiple of 4. Now the cases where X is even but not a multiple of 4 cannot be represented as p square minus q square, because in that case it will be basically sort of some, you know, a multiple of 2, let's say, but not 4, let's say 6 into some odd number. It will be the case which will be, you know, require the product to be represented as even into odd, but we can't afford that the product is either odd into odd or even into even. It should be, you know, representable in one of these two ways, and for that to happen X should either be odd or a multiple of 4, right? Now since X was the product of numbers, we want the product of numbers of a subarray to be either odd or a multiple of 4. Now in the smaller test case, the test case in which, you know, the value of n is less than or equals to 10 power 3, I hope the big of n square solution where we check the product of all subarrays should work. I'm not sure if the sum of, if there is a limitation on total sum of n as well. If there is a limitation then it should work, if not then it might not work, because in that case the time complexity will be big O of t into n square, and we know that t can be up to 10 raised to power 3, so the time complexity will be of order 10 raised to power 9, and it will not work in that case. But if the total sum is less than equals to 10 power 3, then it will work. I'm not sure, I'll just be discussing the larger constraints, the subtask having larger constraints. Yeah, so now we basically want the product odd or a multiple of 4. In other terms, if we write you know, the product as powers of primes or numbers, it should have power 2, you know, it should have at least power 2 of 2. No, it can't be 2 raised to power 1 into something. It should have at least power 2 in its prime factorization. So either product is odd or it has at least power 2 of 2, right? So what can be done to basically check such number of arrays which satisfy one of those two conditions? In this case we know that the product is odd, and for product to be odd all of the numbers should be odd, right? Because if we you know, multiply any number by at least one even number, then the product will become even, and then it will never become odd again, unless and unless we divide it by some even number, right? So all numbers should be odd in this case. Numbers should be odd in this case, right? So in this case this should be the constraint. Now for this to happen, if we consider, you know, basically if we replace the original array values with the powers of 2 it has in the numbers, we basically want that the sum of powers of 2 from L to R for a, you know, for a particular subarray should be greater than or equal to 2, right? That's the case, and this thing can be done in big O of n using 2 pointers, maybe several other techniques as well, but 2 pointers is one of the method. And I need to do it in big O of n, both of these in big O of n, because I tried it during the challenge. Big O of n log n solution is not passing all the test cases. It is giving time limit exceeded on some of the test cases, right? So we'll cover this case and we'll cover this case. We'll add to the answer both of the number of subarrays for both of the cases, and we know that both of these cases will be disjoint. We'll not be counting some subarrays twice, because in this case the product is odd, and being odd obviously means that it is not going to be a multiple of 4, and in this case the product is a multiple of 4. It means that it is not going to be obviously odd, so we can simply add the number of ways for both of these cases, and we'll get our final answer. So let's see how we'll implement these two cases, how we'll implement what we just discussed in code. I've already written down the code. Let's just discuss it once. First I've taken the input of t, which is the number of test cases, then n, which is the number of numbers that I have, the size of the array. Then I just made an array. Mk is basically defined as int star type star arr equals to new type n. Then I'm taking the input from 0 to n minus 1, and if the current number is odd, I'll simply say arr I equals to 0. It means that the power of 2 in this number is basically 0, right? Else if it is divisible by 4, then the power is greater than or equal to 2, right? Then I can simply use the arr value to be 2, because it doesn't matter if the power is 2 or 3 or 4, because all of these numbers are greater than or equal to 2. They hardly make a difference, right? Else the power of 2 is basically 1. Now consider, now just you need to take care. If I would have written it like this, first check for power, if it is divisible by 2, then write this 4, then it would have been wrong, because a number that is divisible by 4 is divisible by 2 also. In this case I would have made a mistake for the numbers that are basically the multiple of 4, right? Now after having done this, I'll initialize my answer with 0, and then I'll basically count the cases for both of the ways, the subarrays with odd product and the subarrays with product percent 4 equal to 0, right? And while calculating the subarrays with odd product, let me I'll basically initialize a counter that will tell me the count of odd consecutive numbers. I'll iterate from 0 to n minus 1. If arr equals to 0, it means that current number is an odd number. Else if I have gotten an even number, I'll simply add to the answer c into c plus 1 by 2, and I'll do c equals to 0, and in the end also I'll add to the answer c into c plus 1 by 2. Let me explain how this is particularly working. Let's say our array was 0 0 0 0 0 1 2 0 0. Now it should be sure that I should not include any number with 1 or 2, because then my product will become even. So I can split the array among this term, about these even terms, to get the continuous odd arrays, right? Now I know that this is an continuous subarray of size 5, and this one is of size 2. Basically the value of c will tell me the size of the last contiguous subarray with all odd terms. Now for this subarray of size 5, if I consider any subarray of this subarray of size 5, that will have only odd terms, right? And that will be a distinct subarray. So for this I'll add 5 into 6 by 2, and for this I'll add 2 into 3 by 2, because for an array of size n, the number of subarrays that it has are n into n plus 1 by 2, right? So by this line number 61, I have included all the cases in my answer which basically have an odd sum, an odd product, right? Now I'll count the subarrays with product percent 4 equals to 0. For this I initialized my r value with -1 initially, and the current sum is 0 because I haven't included anything to the current window for now. Now I am iterating for the left value of the subarray from 0 to n minus 1. Now I'll basically for a given L well, the L value is initially 0 and it will just keep on increasing. For a given L well, I'm trying to find the smallest R value such that the sum from the sum from L well to R well is greater than or equal to 2. If I find the smallest such window that the sum is greater than or equal to 2, I can be sure that for all I belonging to R well to n minus 1, the sum of L well to I will be greater than or equal to 2, right? Because I am only adding some elements, right? But because this is the smallest R value for which the sum is greater than or equal to 2, it will not be greater than or equal to 2. It will basically be less than 2 for all the I values which are greater than this R value, right? Now to do this, what I'm doing is I'm trying to see if the just next R value, if I include the just next R value element, will my sum become greater than 2. I am iterating, making this iteration till the next element that can be included exists. Basically R value plus 1 is less than n and current sum is less than 2, because if current sum is not less than 2, I do not need to include the next element. I've already gotten my smallest R value, right? And if this is if these if both of these conditions are true, I'll simply add to my current sum ARR of plus plus R well. I've increased my R value by 1. It was minus 1 initially because we wanted to start from 0, so I just increased it by 1 and added it to the current sum. Now if current sum is greater than or equal to 2, I'll add to my answer n minus R well, because for every I from R well to 1, from R well to n minus 1, I would have a valid subarray, right? So for the number of numbers between R well to n minus 1 are going to be n minus 1 minus R well plus 1, which is same as n minus R well. So I just added to my answer n minus R. Now in this one for loops iteration, I have calculated the sum, the basically the number of subarrays if my R value, if my L value is equals to this particular L value. Now I need to exclude the value at this particular index from my current sum, right? Now after having done this, I'll simply subtract from my current sum the value at this particular index. Let's try and run it for some test case. So let's try and run it. It will be more clear that way. Let's do this for this array. For this array, the value of powers is going to be 1, 0 and 1, right? And initially my R value is 1 and current sum is obviously 0. When my L value is 0, the indices are 0, 1, 2. I'll do this loop while R value plus 1 is less than n and current sum is less than n. Initially the value of R value is 0, the value of R value is minus 1. Now this when the R value is here, the sum is less than 2, right? So I'll include this to my current sum, so my CS will become 1, and then I'll again move here and I'll include this as well because CS is still less than 1, so CS will again become 1 because I've added 0. Now when I'll move here, when my R value will be equal to this value, I'll again basically include this number and my current sum will become 2. Now the current sum value is greater than or equals to 2, and then I'll add my answer, add to my answer n minus R well. So I'll basically add 1 to my answer, and then I'll subtract from my current sum the value of 0th index, because my current value of L value is 0, so my current sum will become 2 minus 1, again 1. Now my R value is here, my L value is here and my R value is here, right? My L value is here and my R value is here. Now in this case, I'll not even enter this while loop because there is nothing more left to include, right? No matter the sum is less than 2, the sum is still less than 2, but I don't have anything else to include in my current sum. So in this case, the current sum will not be greater than or equal to 2, so I'll not add anything, and I'll subtract from the current sum 0, and my current sum will remain 1 only, and then my LVL will reach here, and then same scenario, I wouldn't have anything to include further, and my current sum will still be less than 2, and I'll just subtract from the current sum the current element, and my sum will become 0, and I'll add 1 to my answer. But there was also one yeah, I was considering this case, right? 2 5 6, there was one subarray with odd sum, the the 5 subarray. So my answer will become 2. One for the case where the product is divisible by 4, and one where the product is odd, right? So I hope it is clear that how both of these loops are basically helping me count the subarrays with odd product and the subarrays with a product divisible by 4 respectively. And the final I'll have the total answer, the basically the number of ways, the number of subarrays found in this subarray, found in this loop, and the number of ways found in this loop, and I'll just simply print it. As we just discussed, this time complexity is going to be big of n for one test case, because in this one I am just running the loop n times, and for this one also after every iteration, the L value is increasing by 1, right? And this while loop in total will run maximum of n times, because I have initialized this r value outside this for loop, and it is going to only run till the value of r val is not equals to n minus 1, right? So the time complexity for this loop is also going to be big O of n. So this will work. This was it for this video guys. I hope you enjoyed this video. I hope the solution code is clear and rendition is clear. If something still is unclear, you can drop down a comment. I'll try to clear it out there. Thank you.